In this tutorial, we are going to design and analyze a steel truss parking canopy for a single vehicle using SAP. First, let's define the structural concept. We will model a truss system similar to the configuration shown here, which is commonly used for lightweight parking shelters. For a typical car parking space, dimensions of 2.5 by 5 meters are usually sufficient. However, in this example, we consider a slightly larger layout for better clearance and constructability. The span of the structure is taken as 3 meters and the length is 5.6 meters. To form the truss geometry, the length is divided into 0.8 meter segments, resulting in 7 equal bays. Now, let's move into SAP and start building the model from scratch. Click on New Model. Before anything else, make sure to set the working units to kilogram/centimeter. Next, select the grid-only option so we can manually define the geometry of the structure. Now we define the grid system in 3 directions: X direction, along the length; Y direction, across the width; Z direction, vertical height. In the X direction, the total length is 5.6 meters divided into 7 segments of 0.8 meters, so we define 8 grid lines. In the next step, we will define the grid spacing in Y and Z directions and refine the vertical geometry of the truss. Now, let's define the material properties. Define gives materials in SAP. We use the default steel material and modify it. Click on Modify, Show Material and rename it to Straight 37 Steel. Now update the key properties. Density equals 7,850. Modulus of elasticity equals to 0.1 times 10 Poisson's ratio equals 0.3. Define the strength values. Phi equals to 1,400. Fu equals 3600. Click OK and save the model as Parking Truss Model. Now, let's continue the modeling by defining the section properties. I select an IPE to 140 section for the main truss columns. For the top and bottom chords, I use box section 100-100. And for diagonal and vertical members, box section 80-40. To define these sections, go to Define Gives Section Properties Gives Frame Sections. Click on Import New Property to select standard sections from the database. Choose Stylized Sections, then go to the European sections and select IP to 140. Next, again click on Import New Property, and this time select Tube Sections. Choose 100-100 box. 80 times 40 box. You can hold Ctrl to select multiple sections at once. Click OK to import all selected sections into the model. Finally, quickly verify that all sections are assigned to ST37 steel. Now, let's start building the truss model geometry. We will model the main column, top and bottom chords, verticals, and diagonal members. Switch to the XZ view and move to Y equals 0 plane. This allows us to draw the first truss in elevation. Select the Draw Frame tool and make sure the section is IPE to 140. We start by drawing the main column. The column connection must be fixed, since the truss acts like a cantilever system. If it is not fixed, the model may become unstable. Now, to create the slope top chord, we need a reference point. We use the Draw Special Joint tool to define a helper point. The truss length is 4.8 meters. And we assume a 5% slope. We round it to 25 centimeters. Now, create a joint 25 centimeters upward in the Z direction to define the top chord slope. For each 0.8 meter segment, the vertical offset is approximately 5 centimeters. So we create intermediate points accordingly. Now, draw the top chord using the 100-100 box section, following the slope. Next, draw the bottom chord. It should follow the same slope and be placed approximately 25 centimeters below the top chord, maintaining the truss depth. To simplify modeling, divide the bottom chord into 6 equal segments. Go to Edit Gives Divide Frames. Now, using these division points, draw the vertical members. You can use Trim, Extend Frame to speed up the process. After that, draw the diagonal members using the 80-40 box section. To complete the truss web system, once the truss is complete, assign pinned connections to the internal members if needed. Now, select the entire truss and replicate it in the Y direction. Distance equals 300 centimeters. This creates the second parallel truss. Next, draw the horizontal members purlins between the two trusses. You can use the 80/40 box section for these elements. To avoid visual clutter, you may temporarily turn off the grid display. Now, assign pinned releases to the purlins if required. Assign gives frame releases. Finally, we will move to modeling the roof covering elements. Go to Define Gives Section Properties Gives Area Sections. Add a new shell thin section. Define thickness approximately equals 0.6 millimeters. Material equals SAP2000. Now use Draw Polygon Area to model the roof panels. Finally, mesh the roof. Assign Gives Area gives automatic mesh. Set maximum element size to approximately 40 cm. Now, we move to load definition, which is one of the most important steps in structural analysis. The main loads in this structure are dead load, wind load, snow load. There is no live load considered for this canopy. First, go to Define Gives Load Patterns. Define the dead load. Type equals dead. Self-weight multiplier equals 1.0. This allows the software to automatically calculate. Next, define wind loads, since this is a monoslope canopy. Wind can act in different directions. So we define two cases, wind 1, wind 2. These represent different pressure and section conditions. Also define a snow load case, if required by the design. After defining load patterns, SAP automatically creates corresponding load cases. You can verify them under Define Gives Load Cases. Now we define load combinations based on design codes. Go to Define Gives Load Combinations. We will use the following strength combinations. Combo 1, 1 point for dead, combo to critical. 1 point to dead plus 1.6 snow plus 0.8 wind. Since wind can act in two directions, we create this combination for both wind 1, wind 2. Another important combination, combo 3. 0.9 dead plus 1.6 wind. This is critical for uplift conditions. We ignore seismic load combinations because wind governs this type of lightweight structure. Now, let's define service load combinations for deflection control. Typical service combinations. Service 1, dead. Service 2, dead plus snow. These combinations are used to check deflection limits, which must satisfy code requirements. Now, we move to load assignment, starting with wind load. In this model, the horizontal members purlins transfer loads from the roof sheets to the trusses. So instead of applying loads directly to the truss, we apply area loads and let the software convert them into line loads on purlins. The idea is simple. Surface load times tributary width equals line load on each beam in this model. The tributary width is approximately 0.8 meters. Now, select all roof panels and go to Assign Gives Area Loads Gives Uniform to Frame. Before applying wind load, we must understand local axes. Each element has its own local coordinate system. Local 1 red, local 2 green, local 3 blue. Turn on local axes from Set Display Options gives local axes for correct one-way load distribution. The load direction must align properly with the purlins, so we rotate the local axes. Go to Assign Gives Area gives local axis rotate by 90 degrees. This ensures the load is applied perpendicular to the purlins. Now apply wind load. Load pattern equals wind 1. Coordinate system equals local. Load direction equals local 3. Distribution equals one way. Enter the value 0.145. Make sure your units are consistent. Repeat the same process for wind 2, but with section negative pressure, minus 0.280. Now, apply snow load. Go to Assign gives area, loads gives uniform to frame. Set load pattern equals snow. Coordinate system equals global. Direction equals gravity projected. Enter the snow load value, 1.98. This ensures the load is applied correctly on the sloped surface. Now all loads are assigned. Save the model. Now let's calculate the wind load based on ASCE 7 provisions. The main parameter is the velocity pressure, which is defined as. Substituting into the equation, we obtain approximately. Next, we apply the external pressure coefficient Cp. For a monoslope canopy, according to ASCE 7, the design wind pressure is calculated as. These values are then applied in the model as wind 1 pressure, wind 2 section. This approach ensures that both critical loading scenarios are captured in the analysis. Wind section is usually more critical for lightweight structures. Now we proceed to the structural analysis stage. From the Analyze menu, select Set Analysis Options. Since this is a three-dimensional structure, we choose Space Frame Model. For this type of structure, wind load governs over seismic load. So we neglect seismic effects in this model. Turn off local axes display for clarity. Also enable deformed shape plus contour display for better visualization. Save the model and run the analysis. Analyze gives Run Analysis. Now we move to the design stage. Select design code AISC360. Set the frame type as IMF Intermediate Moment Frame. This is suitable for such lightweight steel structures. Set the demand capacity ratio limit to 1.05. This allows a small 5% tolerance in design. Go to Design gives Select Load Combinations. Select COMB1 to COMB4, excludes service combinations. Now run the design check. Most sections pass successfully. From design results, columns IPE 240, OK. Box beams 100, 180, 40, OK. Truss members, OK. Now check displacement. Display gives deformed shape. The allowable deflection is, for a span of 3 meters, we get allowable deflection approximately equals 12.5 millimeters. The maximum deflection from analysis is 17 millimeters global displacement. But the relative deflection of the truss itself is approximately 5 millimeters. So we distinguish between total structural movement. Relative truss deformation. The critical value is the relative deformation, which is about 5 millimeters. The structure is completely acceptable in serviceability. Also, all members satisfy strength requirements, so the final design is safe and approved. Now that the structure has passed both strength and displacement checks, we move to the overturning stability verification. For lightweight structures such as canopies, wind-induced overturning is a critical design case. The structure must remain stable against uplift and lateral wind forces. The stability condition is defined as resisting moment is greater than or equal to 1.75 times overturning moment. From the analysis results, we extract the maximum base moment. Load case 1, 0.27. Load case to critical, 0.52. So the governing overturning moment is 0.5 to 10 meter. Now we design a foundation block under each column. Size equals 1.2 times 1.2 times 0.6 meter. We check whether the resisting moment from self-weight is sufficient. The resisting moment is calculated from concrete self-weight. Lever arm equals half of foundation width. Unit weight of concrete. After calculation, resistance moment greater than 1.75 times 0.52. So the foundation is stable against overturning. Now we move to structural optimization. From design results, we observe that several members are over-designed. Display PM ratio demand capacity. We notice columns gives OK, beams gives OK, truss diagonals gives very low utilization. This indicates that some members are not efficiently designed. especially diagonal and vertical truss elements. We now reduce section sizes from box 80/40, 100/100 to box 60/40 smaller section. Update sections via Define gives section properties gives frame sections. Reassign sections to diagonal and vertical members, then rerun analysis. After reanalysis, stress ratios increased, but remained within allowable limits. Deflection remained acceptable. This confirms that the structure is now more economical and optimized, while still satisfying both strength and serviceability requirements. The final design is structurally safe, economically optimized, serviceability compliant. Optimization is an iterative process. This is a safe and optimized steel truss canopy design.